now let's move on to the different chemical approaches which are being used. So again, for the chemical approach, there could be two things. Either you are using a bottom up approach or you are using a top down approach. When we talk about top down approach, we talk about etching. So you have a bulk material, say for example. So again, the two options you have, either top down or bottom up. So whatever be the technique, when we are going about top down, we are talking about etching. Etching, in a sense, you are taking a bulk material and using some kind of acid or some kind of other chemical, you are bringing down the size of it because of abrasive chemical action. And when we talk about the bottom up approach, we mostly talk about self assembly of particles in the presence of capping agent and other agents to promote self assembly. So let me just differentiate it. Okay, now talking about the chemical methods which are being employed, they fall under so the chemical methods are falling under these headings. So they have sol-gel synthesis. You have a sol and have a gel. We'll talk later about the detail of these kind of synthesis. You have sol-gel synthesis, then you have microemulsion technique, followed by hydrothermal synthesis, then you have polyol synthesis, followed by chemical vapor synthesis, then we have plasma enhanced chemical vapor deposition. Plasma enhanced chemical vapor deposition. So these are some of the broad classification of chemical synthesis of nanomaterial: sol-gel, microemulsion, hydrothermal, polyol synthesis, chemical vapor synthesis, and plasma enhanced chemical vapor deposition. And if you look at these methods, the last two, like chemical vapor synthesis, plasma enhanced chemical vapor deposition, even hydrothermal synthesis, all these techniques requires fairly high energy. These are energy intensive, just like your physical methods where we talk about these techniques where you need significant amount of energy. Here we are talking about high energy intensive processes. On the contrary, when we look at these two techniques, sol-gel or sol-gel synthesis, microemulsion technique, these in comparison, with respect to it, comparatively these are low energy intensive processes. Once we will talk in detail about this, we will highlight this fact, why some of these techniques are low energy requiring, whereas the other ones are high energy requiring. So now we have discussed as of now, or enumerated as of now, the physical and the chemical synthesis routes. Now from here we'll move on to the biological route. Now when we talk about the biological route, why it is so critical that we understand the biological route? Well, if you look at nature, the way nature functions, let's take a simple example that plant world is the only place or only kingdom which can fix the nitrogen from the environment. There is no other way you can fix nitrogen, and there are these enzymes called nitrogenase which can trap the aerial nitrogen and convert it into some usable salt, some usable form. And that's why we are completely dependent on nitrogen fixing microbes which have a symbiotic relationship with legumes and other plants. So they are the ones which enriches the soil of nitrogen. Otherwise there is no other way you can do it. Now even as a layman, if you think of it, plant does not have a chemical vapor deposition technique or laser pyrolysis or some hydrothermal synthesis or any of these sophisticated, so-called sophisticated energy intensive tools to achieve this feat. What it does, it has developed a genome of it, and it synthesized some very unique enzymes which could assist in transforming, tweak around with these bonds of getting the nitrogen gas and transforming it, attaching it with some factor, so it assists in it and ensure that we get the desired result. But this it does in a simple room temperature, or maybe I am at this point sitting or delivering a talk at around 20 degrees centigrade, the temperature of the room. Outside will be like 30-35 degrees centigrade. So within the physiological limits, a plant can do this. So in other words, plant does these things without any extra requirements of energy in terms of high energy requirements or very sophisticated tools. So in other words, nature is our best guide to understand what we call as bottom up approach of nanoparticle synthesis, as well as nature can teach us how it does the top down approach. Because think of it, when we talk about a top down, so what we are talking about, we have a bulk material out here. Now suppose this bulk material is under the influence of a microbe. This microbe, if we could increase the population of the microbes on it, this can bring it down to small particles over a period of time. So it is possible that it could leach out the particle, or it may consume it. But then if we get this microbes which has consumed these particles and grind it together, that will be much more less intensive process, and pull out those particles. So are these feasible? Could we think in that way? Or as we discussed just now, in a biological world, the bottom up approach. So these are the principle or guidelining feature what provokes us to think that biological route of nanomaterial synthesis is the future where we could emulate nature, emulating nature because why we wanted to emulate nature is basically biosynthesis, or which is a green synthesis. You are not using any caustic acid or any kind of caustic compounds or any kind of harsh environment to achieve this kind of synthesis, yet you achieve your goal. So what biology has to offer is, what we have to learn is understanding the nano reactors or nano vessels, where in a confined space enzymes execute the addition and subtraction of bonds, and thereby bringing about a self-assembly. Or even at times these enzyme could catalyze, executes the breaking of bulk, thereby leading to small particulates. So in other words, what we are talking about in terms of biological root is, we have to understand. So most of these provides environmentally benign. What we are is basically environmentally benign, low toxic, cost effective, and fairly efficient modules of synthesis. And the biological routes which are currently widely explored includes microorganism assisted biogenesis, microorganism assisted biogenesis is one. The second thing is biotemplate assisted biogenesis, and we'll talk in detail about this as we'll be progressing in this area. Biotemplate assisted biogenesis, plant extract assisted biogenesis. Assisted biogenesis. So the logic is simple. What is being followed out here is this: employing biological systems, employ biological systems like bacteria, fungi, viruses, which is kind of a bit tricky. Viruses, yeasts, actinomycetes, and plant extracts to bring about the biogenesis or synthesis of these kind of nanomaterial. Now, one thing must be realizing what you are essentially doing. The key idea is kind of, if you look at it, much of these research in the initial area of research out here are of you are trying to extract much of the enzymes from these systems, which will help in the synthesis of the nanomaterial. Now, one area which flourished in last 30-40 years, where a tremendous amount of research has taken place, is in the area of bioinorganic chemistry. So, if you look at the work which has been carried out in bioinorganic chemistry, you will realize there are people who have tried to model minimal unit of atoms needed to mimic the function of an enzyme. There is tremendous amount of work which has gone in synthesizing such, or say for example modeling nitrogenase, modeling, these are just some of the examples I'm giving, modeling water splitting clusters, which is mostly consist of manganese cluster essentially. So these are the approach which has been there, but not under the banner of nanotechnology, which has been there, where people have, say for example, just to make you understand, say for example when we talk about an enzyme, so we talk about a huge protein moiety, and within that protein moiety you have active site. Say for example this blue is showing the active site, okay, and say for example this is an example of say nitrogenase we are talking about, okay. So this is the active site of nitrogenase. Now what people have been trying is, this is the site where say nitrogen gas is coming, or maybe some another site it is binding, and then there is a reaction which is happening and leading to transformation of the nitrogen, and of course the enzyme is not getting used up. What people are trying to do for a while, say for example they wanted to understand this structure in atomic resolution, and once they understand this structure in atomic resolution, what they try to do, they wanted to synthesize this structure outside the system, not by biological route, by simple inorganic route, could get it in an inorganic route, then you can, and if it is a stable inorganic approach, a stable route, then you can actually produce, or you can transform nitrogen to your desired product in a controlled environment. So if one can achieve these desired product, okay, then much of our synthesis of urea, ammonia, those high energy processes will be kept at bay if we understand this. So in other words, what I wanted to highlight here is this: nanotechnology, of course, under the banner of nanotechnology, these were not there. This is one of the key areas of bioinorganic chemistry. But if you look at some of the development of bioinorganic chemistry, and if you follow up with the people even in India as well as abroad who have worked extensively in this area for last 20 to 30 years, you will realize that they are nothing but figuring out low energy methods, modeling enzymes to create environmentally benign route to fix different kind of compounds which are needed for agriculture. Today we are kind of standing at that beautiful niche to realize and appreciate the research which has undergone for last multiple decades in the area of bioinorganic chemistry. So here I take the liberty to say much of these bioorganic chemistry research of modeling the enzymes and synthesizing them is kind of laying the foundation stone of modern roots of biological based systems for nanomaterial synthesis. That's kind of is where much of these biological routes are heading. They are very, very energy efficient systems. The way in the photosystem 2, the manganese cluster which traps the water molecule and split up the water molecule to generate hydrogen and oxygen is just a magic. There is no system which could do it so very efficiently. Not only that, think of the water channels. If you could emulate water channel in terms of water purification, think of the way a nitrogen fixing bacteria or microbes traps the nitrogen from the air, aerial trapping. So these are some of the marvels of biology, and that's why I mentioned in the beginning, the idea is to, this word is critical for you people to appreciate, emulating nature. This is where lies answer to most of our tricky questions, which otherwise is not easy to answer by any means. Emulating nature, the way nature does. And if we understand nature, the way it does it, then one day probably much of these techniques will merge towards biological techniques, which, in other words, which will be much more precise. It's a very precise route and these will be in terms of the energy out here. If you compare it, so these will be energy low technique as well as small amount of raw materials will be needed and will be much more eco-friendly. But these biological methods are just in their infancy. We are slowly, very slowly realizing that what all we can do using biological tool. And this is, I'm not talking about genetic engineering, I'm talking about slightly different, that whole domain of bioinorganic chemistry and its application in nanomaterial synthesis. So this is broadly are the different methods under the heading of physical, chemical and biological methods of synthesis. We'll go a little bit after this in explaining very briefly about what is high energy ball milling, what is pulse vapor deposition, what is laser pyrolysis, what is flash spray pyrolysis, what is electrospaying and melt mixing. Then in the chemical route, we will talk about the sol gel methods, microemulsion technique, hydrothermal synthesis, polyol synthesis, chemical vapor synthesis, plasma enhanced chemical vapor deposition. And then in the biological routes, we will talk about the microorganism assisted biogenesis, biotemplate assisted biogenesis and plant extract assisted biogenesis. Okay. So, we will close in here. In the next class, we will talk in detail about these techniques. Thank you.